Okay, sorry about that. I had a technical glitch in recording the previous segment. Things died just before I got to discussing two-dimensional motion. So let me go over what the high points were. Um, Main thing that I did here in this first bit, just with no air resistance, is the system has now been changed to have an X component. So again, here we've got this is the Y component here, and I have G being a negative number, so that takes care of the direction there. And then the X component here, I, for the moment, have no X component of acceleration because I've got no forces other than gravity. So when we set up our ND solve, it's just the same as before. I go ahead and now pass it the system, and now I need a few more initial variables. So this is the launch angle here, or the X component of the velocity here, the Y component, the velocity there. So now I'm asking it to solve for 4 thines, and it indeed returns 4 thines here. Okay, now this plot here is just a plot of the speed as a function of time. So you can see, sure enough, at the turnaround point, the speed is at the lowest. At this point right here, it would all be in the x direction. And then this is a plot of the trajectory. You see our classic introphysics parabola. Okay, now to introduce air resistance, I'll just go ahead and add it to the system. Now here, this would correspond to the y component of our linear air resistance. Just take the y component, multiply it by minus C1. Same for the x component over here. I go ahead and run it through. And you can see there is a slight shift. The curve is a little more, kind of goes clunk a little faster down on the return side. Then to take it a little further, I went ahead, or maybe make it more realistic, one might say, I went ahead and changed that to quadratic air resistance. Again, here, this is the tricky bit here. So now this bit here with the square, so I changed the C1 to a C2, and I left in the bit that gives me the component. But then here, this is the absolute value of V, and I actually need the absolute value of V. That's why solving this analytically is basically can't be done, is because you wind up with this heinously coupled set of differential equations that involve powers of each other. And there's just no clean way to break that apart. But it falls apart to numeric attacks quite nicely. Without this magnitude of the speed, or without this speed term in here, the coupling would be gone, and it would be quite straightforward to solve analytically. Okay, and you can see that the behavior is even more pronounced of a clunk down on the backside. So we keep ending up shorter and shorter off of the ideal. And then just for the giggles, I combine the two. You can tell that the quadratic dominates. The linear might have a little bit of an effect right in here, but even I'm having a hard time seeing that. So that's the result there. Next series of videos, we will be going into the world of oscillations.